so we can. All right, I'm gonna kick it off. Hello, everyone. Thank you for coming to the No Jargon Talks, session 3. We have two Astro speakers today, Brian Pardo and Samir Patel. Brian Pardo is a graduate student in the Department of Physics and Astronomy at the University of Pittsburgh, and Samir is also a graduate student, but in University of Iowa. This is the first time we are inviting a speaker outside Pitt. We are excited to have them. We are going to use this very cool app Slido in case you want to ask questions after a speaker has given talk anonymously. Please go ahead and click the link. I'm going to post that in the chat box. That will help you ask questions. And you're at the same time very welcome to just unmute yourself or use the raise hand emoji and the Zoom to ask any questions. We will have you unmute and you can go ahead and ask. The speakers would be given 15 minutes for the talk, and you will have 10 to 15 minutes for the question and answer session for that. Without any further ado, I'm going to introduce our first speaker, Brian Pardo. Brian is a fifth-year graduate student supervised by Adam Libovich. After completing his undergraduate degree at Boston University, he took a winding path back to physics, working as a copy editor, competitive climbing coach, and commercial salmon fisherman before coming to the University of Pittsburgh. Very interesting. He is interested in the intersection of particle physics and gravity, including particle dynamics in the early universe, scattering amplitudes, and gravitational waves. When not doing physics, he loves working on art projects and being outdoors in any way possible. Very amazing. I'm gonna give it over to you, Brian, now.
Okay, thank you for the introduction. I'm gonna see if I can figure out how to share here. Okay, can everybody see this?
Yep.
All right. Okay, so the title of my talk is Extremely Quiet and Incredibly Distant, a little play on a Jonathan Safran Foer novel, and I'm going to be talking about searching for gravitational waves and what we can learn from them. So first of all, I just want to say thank you to the Women and Minorities in Physics organization for hosting these talks. It was a nice challenge to try and come up with something that was hopefully understandable and clear for people that don't do this every day. Okay. So gravitational waves at a glance. So this is sort of the outline for my talk. I'm going to try and answer the question, what is gravity, at least for the purposes of what I'll be talking about. I'll try and talk about what a gravitational wave is and what makes them. I'm going to talk about how to see a gravitational wave, how we detect these things. And then I'll talk a little bit about how my research fits into all of that. And I'll try and answer what I think is an important question is, why do we study these things and why do we care? So let's start with what is gravity? So if you've taken an intro to physics class, you've probably thought of gravity as a force that you always add when you do projectile motion and things like that. So here I have a cat, it's sitting on the surface of the earth and it feels a force, and we represent that with an arrow. And this is a very classical Newtonian picture of physics. And I'm going to ask you to put this aside, and we're going to rethink what we imagine when we think of gravity. So let's start with without the Earth, and we'll just have open space. And in open space, I want you to imagine a grid, and at every point in the grid, there sits a clock and a ruler. And if there's no objects, no massive objects, all the clocks and all the rulers can tick at the exact same rate. Okay, so if I have a cat here at the bottom, and the cat is moving at some speed, it's going to keep moving in a constant motion at a constant speed. Now, if I now add a massive object, like for example, the Earth, what you see is that the clocks closest to the Earth are going to actually change how fast they tick relative to an observer that's very far away from the Earth. And that changing in the ticking of the clock, they're going to tick slower that's what we call curvature. And what curvature does is it bends the trajectory of objects. So now with this curvature, this changing of the clock nearer to the Earth, when the cat is moving at a constant speed, or what it thinks is a constant speed, it's going to take a curved trajectory. And so when we talk about gravity, gravity is that bending by a massive object. And so what we say is that space-time tells matter how to move. In other words, the changing of the clock tells the cat to go in a curved trajectory, and matter tells space-time how to curve. So space-time responds to the addition of a massive object. So the addition of the Earth changes clocks, or it can stretch or shrink rulers. So a picture of this with the sun and the Earth, the sun creates a disturbance in space-time, a bending of space-time. And here we have the Earth. So the sun creates this deep depression, and the Earth moves around the sun. Now, the interesting thing here is actually this depression, this bending is actually in time instead of in space mostly. And so the Earth actually is responding to a difference in time closer to the sun. So kind of like an interesting thing that happens there. Okay, so now we have a picture of what gravity is. It's this quickening or slowing of clocks and stretching and contracting of rulers. So what is a gravitational wave and what makes them? So a gravitational wave is just a traveling stretching and contracting of rulers, or a slowing or speeding of time. And what causes this to happen is when you have massive objects that are bending space and time, when they move, they create a disturbance. So for example, the Earth traveling around the sun in a motion like that pushes this disturbance of clocks and rulers. And it's not that different from, for example, a duck on water. You see a wave-like disturbance that travels outwards away from this duck. And you can think of those ripples as increased speeding and slowing of clocks, or stretching and contracting of rulers. Now, the interesting thing and the analogy I'd like to make here is if you're far away from this duck and you see these ripples, you can look back and say, there's something that was disturbing the water, and you may be able to even figure out how big that object was, how fast it was moving, and things like that. And you may even guess that it was a duck. Okay, so we're going to do the exact same thing with orbiting objects, in this case, two black holes. And the only thing you need to know about a black hole for the purposes here is that clocks actually are so slowed as they get closest to a black hole that they actually come to a stop at the surface. So it's hard to picture that, but just keep that in the back of your mind. And let's see what this looks like. This is a little film. So as these black holes orbit, they push and they push these disturbances, and what you can see as these ripples is a stretching and contracting of rulers that becomes even more pronounced as the objects get closer and closer until they merge into a single object and there's no more disturbance. Okay. So that's what a gravitational wave is. That's what makes them, orbiting objects or accelerating masses. How do we see them? The way that we see them is that we use what's called an interferometer. And an interferometer is a very clever object, a detector. And we start with a laser on the left. The laser generates light waves. Those light waves project onto a beam splitter, which splits the light wave into two. One goes up, one goes to the right. That light wave reflects off of a mirror on either path, and then I recombine them at the detector. And depending on the relative length of the arm, the light waves either add or subtract, and that forms a signal. And we can see, we can measure essentially the expanding or contracting of rulers along these two different directions. And here we see an actual detector. This is a detector called Virgo. It's in Italy. Here's one arm, Here's the other arm. That's the path the lasers travel, and then the detector is inside this building here. Now, these arms are 3 kilometers in length, about 2 miles long. And the change in length along that whole length, the relative stretching or contracting of those rulers is really small. It's of order 10 to the minus 18 meters, or 1/1000th the width of a proton. So there's a lot of clever engineering and specifics that go into here, which are outside of my realm of expertise. Lots of PhDs have been done on how to do this. So lots of work there. But when you detect that signal, what you end up with is something that looks like this. So we see that this is the signal that you read. And when you reconstruct it, you can see that this is the stretching the relative stretching of the rulers along those 2 arms. And so this is the point where the black holes start. They start to orbit each other, or they're orbiting each other. The orbit gets smaller and smaller as they lose gravitational waves. Those gravitational waves get large or get stronger as the black holes merge, and then they merge into a single black hole. And we end up with something, and what we want to do is, using this very simple signal, we want to reconstruct what the event was, the full event, and all of its complexity, and hopefully learn things about the masses of the black holes that were involved, their spins, and things like that. And so what my research is generating these models, this black line here, which we can use to analyze the data. Okay, so what is my research? And I'd like to make a little analogy about what I specifically do, because these are incredibly complex systems, and we want to be able to simplify them in a way that we can understand. So I'm going to make an analogy. Here on the left, if we look at this, we see some very complex fibers, which sort of are arranged randomly. And this is an electron microscope picture of paper. Now, if you zoom out a little bit, you can see that those fibers are arranged into some pattern. And if you zoom out even more, you just see paper. And I want to be able to figure out the properties of paper, how it tears, what it feels like, its color, things like that. But I don't want to have to go through all of the complexity of the system in order to do that. So what I can do is I can understand this underlying picture. I can average over these fibers and match these different scales so that what's on the left is encoded at each level. So I can take what's here, I can encode it so I understand it, and match to here, and then I encode and get to here. And I match the properties between these scales so that these different scales, so I can learn about the underlying scales from just learning about paper. Now we're going to do the same thing with our black hole system. So we're going to start with the full complexity of the system. And what I'm going to do is I'm going to zoom out a little bit and look at this system as 2 point objects, which are orbiting each other. And then I'm going to zoom out even further to the gravitational wave scale. And what I see is that I can't even see the individual black holes. I just see a black box with some sort of complexity inside of it. And I see the radiation, which is what I want to detect. Now, mathematically, what this looks like is there's all these complex processes, and each one of these diagrams represents a mathematical structure which encodes that complexity. And when I add all of those things up and average, I sort of throw this into a structure. I turn the crank, and what I get out is actually the picture that I want. And so this is the close-up scale, and then this is the long scale. And the mathematics of it connects those 2 scales. Okay, so that's sort of an overview of my research. Why do we care about any of this stuff? Well, studying these systems allows us to ask the question, is Einstein's gravity complete? We're calculating with Einstein's gravity, or general relativity, and we can compare what we measure to our expectations based on Einstein's gravity. And if there's variations, we know that there's probably more physics. We can study black holes directly, which is one of the few ways that we can do that, because these are systems that are built on black holes. And we can actually study the shape of black holes. We can look at whether black holes have so-called hair or information beyond just their masses and their spins. We can learn about the formation of black holes and their binary systems or pairs of black holes, and from that learn about how black holes are formed. We can actually do some clever things like measure the expansion rate of the universe by comparing merging black holes nearby and really far away. We can investigate quantum gravity, and we can even study the structure of nuclear materials if the colliding objects aren't black holes, but are instead things like neutron stars. And the thing that I think is the coolest, but maybe the least practical, is we can learn some surprising things about the structure of space-time and gravity. And there are a lot of surprising mathematical structures that emerge from that really big mess of diagrams that we compute. So thank you for your time. Thank you for listening, and I'll open up to questions.
Thank you very much, Brian. So we have the Slido link posted in the chat if you guys want to write out your questions. But we're also open to, you can like unmute yourself and ask a question. So questions are open. I see someone raise their hand.
Yeah, I was hoping to find out just how you get to measure something, this difference between a thousandth of a width of a proton. To me, that just seems like magic. Is the signal clear enough? Because it seemed kind of squiggly to really determine really detailed things about gravity.
Yes, the answer is yes, it is clear enough. And that is a really good question. One of the interesting things about this research is that different things enter at different levels of precision. So just even seeing that the orbit decays, that the black holes approach each other, is a very, very, very fine effect. And it comes from actually the back reaction, the waves that are generated, basically back reacting on the black holes themselves. So these are things that we would never be, even just that the fact that they merge is not something we would be able to measure in our solar system. So yeah, you get lots and lots of very fine effects that you can measure. Does that sort of answer your question?
Oh yeah, thanks.
I actually have a question going off of that. What do you mean by back reaction?
Yeah, so you see this in electromagnetism too. So if you have a charged particle and you accelerate that charged particle, it will actually slow itself down by radiating electromagnetic waves. And that's called radiation reaction. So it actually shows up in Jackson at the end. But yeah, accelerating objects actually radiate their own energy, and it's sort of a back reaction.
Thank you.
Yeah.
Okay. Are there any other questions from the audience? We do have a question on the Slido. So someone asked, do these gravitational wave detectors need to take into account the curvature of the Earth since their arms are so long?
Yeah, I don't know a lot of the details of how these detectors work, because I do theory, and there's so much to it, but I'm assuming that yeah, the answer is probably yes. Although I'm not sure because they're laser beams. Yeah, I don't know. Yeah, I don't know. There's so much that goes into the engineering that is a mystery to me, that I'm just as curious about.
Thank you. Okay, any other questions in the audience?
it's cool what you said, that is you put the clocks close to the surface of a black hole, they slow down. But if you fall into a black hole, it happens pretty painfully quick.
I have a quick question. So you mentioned like detecting like mergers of neutron stars as well. Are there any other systems that you can't detect? Because I imagine anything like less massive than that, the gravitational waves would be too small to detect, or I don't know.
Yeah, that's a really good question. And I think it's a question that a lot of people ask because there's lots of other systems that people find interesting for lots of different reasons. The really big limitation on what you can detect isn't so much how small the waves are. It's actually surprisingly what the frequency is. So the frequency of what you can measure is determined by how long the arms are of the detector. So Earth-based ones, there's a very narrow band of, they call it a band of frequency. So what your range of what you can see. So if you were to go to something like a smaller set of stars, you wouldn't necessarily be able to see them. But there is a future detector called LISA, which is a space-based detector, which the engineering of it is so cool and mind-blowing and futuristic. But basically you put the detector arms up in space in orbit. And so you have much longer arms, which allows you to go to much lower frequencies. And then you'd be able to detect other things. Yeah. Does that sort of answer the question? Yeah, depending on what you're trying to, what you end up measuring, you learn completely different things, which is, I think, the most interesting thing, one of the more interesting things. Because if you study black holes, you're really, we have lots of interest in black holes, but neutron stars, when you measure them, you learn a lot of things about surprising things like where do elements come from, and things like that. And if you go to smaller objects, you might be able to learn things about how things reside in galaxies and how stars form and things like that. So yeah.
That all sounds really great. Very cool, Brian. Are there any last questions? And we're going to be posting this recording on the YouTube as well. So if you're interested in rewatching it, going back over details, we'll have it on our website and link it there as well. Okay. If there are no more questions, can we all just thank Brian for this presentation? Silent claps. All right. And we can follow up. Okay, well, we have a feedback form for Brian. So because this is a no jargon talks, we want to provide feedback for the speakers, kind of assessing, how they did, avoiding jargon, clarity, and whatnot. I think Yasha, do you have the link to that?
Yep, I'm gonna post that feedback form link on the chat box right now. Yeah, please consider taking a minute and giving the feedback. That's super helpful for all the speakers. Thank you so much, Brian. That was an amazing and so informative talk. Really enjoyed it. Get to know so many things without using any jargons. Let's move on to our second speaker for today's session. We have Samir Patel from University of Iowa. Samir started his journey in science as an engineer. He moved on to physics as a master's student and began working in the domain of astroparticle physics in grad school. He worked for a NASA code package that is designed to simulate the air showers for space-based missions. And he's also a Veritas collaborator in gamma ray astronomy. Very cool, Samir. Over to you now.
me share my screen. Okay, can everyone see my slides?
Yep.
Oh. Okay, so hi everyone. I'm going to be talking about multi-messenger astronomy. So in other words, how to actually view the universe in anything other than light particles. So we know that we can observe the universe using photons, the light particles, but it turns out that you can use other high energy particles such as what Brian talked about, gravitational waves. And we can look at the universe using neutrinos. We can look at the universe using cosmic rays for that matter. So since I consider myself a theorist and I've been warned about the no jargon things, I'm gonna clear up the space by pretty much talking about the little jargon that I have in the few earlier slides, which will be important as we move along. So this is kind of what you would see in a introductory particle physics class. You see the standard model of the particles here. We know, everyone knows what an electron is. So building from there, electron is a part of a family called leptons. You have the heavier counterpart called muons, and you have taus. And for each of these three leptons, you have an associated neutrino. And these neutrinos are electrically neutral, unlike the electron, muon, and tau, which are negatively charged. The neutrinos hold no charge, so they do not interact in any electromagnetic processes. And they only interact through the weak interaction. So this makes them very difficult to detect. And I will talk about this later on as well. And if you look at the masses, which is here on the upper left corner of the boxes here everywhere, you would notice that the masses of the neutrinos are very small. They're in MeVs. And up till this date, it's an open question in particle physics about the masses of these neutrinos. And we only have upper bounds, meaning the masses can only be lower than these values. The reason for this is something called neutrino oscillations, which you may have heard about. And it's interesting that when neutrinos oscillate through space, they can change into one of the other flavors. And by other flavors, I mean the electron neutrino can change into muon neutrinos, the muon neutrinos can change into tau, or tau into electron, and so on and so forth. And apart from changing into these flavors, they can also change into their associated antineutrinos. So there's kind of 6 possible flavored combinations that you can make when they propagate through space. Now, I'm going to be focusing more on taus in the later parts of my presentation, because I work on taus and tau neutrinos as they will come from any astrophysical objects when there's like a supernova explosion or anything that happens, and when they reach the Earth. So what taus are among the heaviest of the family of the leptons, and they have super high penetrating powers. That's because of their heavy mass. If you look at their mass, they're like they weigh like 1.77 GeV. So however, this penetrating power only appears at ultra high velocities that are very close to the speed of light, and this happens at PeV energies. So you know the standard generation of energies, such as electron volts, you have kilo electron volts, you have mega electron volts, you have giga electron volts, that's GeV. Above GeV, you have TeVs, and above TeVs, that means 1,000 TeVs, about a PeV, that's a peta electron volt. And the highest penetrating power of the taus only appears at these PeV energies. So just keep that at the back of the mind when I move on. And one thing to note is also, whenever a tau decays, it always creates a tau neutrino. Among the other things that it creates, there's always a tau neutrino that decay. This will be important for the stuff that I cover later. So moving on, this is how you actually look at the universe if you looked at the cosmic microwave background radiation coming from the early parts of the universe. So we know what the cosmic microwave background radiation is. It peaks in the radio and the microwave spectrum of the light. So this is what you would see. These are the small anisotropies of the different areas of the universe, meaning it's somewhat a little bit hotter compared to some places in the universe which are a little bit colder. And this is what cosmologists essentially study. And you can see the view of the universe if you look at the radio or the microwave in the microwave regimes, and this corresponds to a wavelength of photons about 1 millimeter, or equivalent to an energy about 10 to the minus 4 eV electrons. Next, we move on to the optical sky. Now, optical astronomers study this all the time. So this is a galactic view of the universe. So you see the galactic belt of the of our galaxy here, so to speak. So you see that there's a lot of dust in the band of the Milky Way here, and that's because there's a lot of activity going on near the center of the Milky Way here. And this image corresponds to the view if you were to look through an optical telescope in the range of 10 to the minus 6 meters, or of about one electron volt. Next, we have, moving to higher energy gamma rays. This is the view of the universe in gamma rays. So this is something that you would look if you were to view the universe using some telescopes that are on the Earth called imaging atmospheric Cherenkov telescopes, which Veritas is a part of. So they actually detect gamma ray radiation coming from sources in the sky. As you can see here, the red bands correspond to the highest activity, again, in the near towards the galactic center, or the galactic band. And this is mostly because of supernova remnants. They actually radiate through these high energies and photons, and the dots that you see on the other sides are mostly what are called active galactic nuclei. And those are essentially the very highly energetic centers of galaxies that have jets coming out from them. Sometimes when you view them head on, they're called blazars, and those show the highest activities in these areas. And this corresponds to an energy of 10 to the 9 eV, or 10 to the minus 15 meters, or wavelength of 10 to the minus 15 meters equivalently. Now, funny story. This is how the universe would seem like if you were to view it in the very highest energies of photons. Nothing, right? So the reason for this is the universe is opaque to the most highest photon energies that are coming from sources. Now, the reason for this is because when they come from the astrophysical sources, they are unable to reach the Earth because they get absorbed by the CMB photons, or the cosmic microwave background photons, which I talked about earlier. So they would never probably make it to the Earth to observe, and hence we cannot actually view the universe in these high energy photons. And this corresponds to about a PeV. So if you were to look at the universe about some PeV photon energies, you would see nothing, because they would all get absorbed and backscattered. So this brings me to the next important question about how do we actually view the universe at these high energies. So you can not only view the universe using the photons, which I talked about, but you can view the universe using neutrinos. You can view the universe using cosmic rays and gravitational waves, as Brian discussed earlier. So you can see the different astrophysical objects emitting radiation through these different messengers or particles, and it essentially provides you an extension of the energy window through which you can observe the universe. So shown here is a very generic, mostly it looks like a active galactic nuclei, and it's shooting a jet from its center. And you can see the different particles that are coming out from this jet. You can see the photons that actually create these air showers, and I will also go through this in the later part of my talk. When you have gamma ray photons, they actually get absorbed by the Earth's atmosphere. So in order to view them, you cannot view the gamma ray photons directly, but you have to actually observe the secondary air shower particles that they create in the Earth's atmosphere. You have the neutrinos, and by the virtue of their property that they don't really interact with anything, they mostly go through the Earth without being even noticed. And then you have the proton, which we know is charged, positively charged, right? So this happens to be a problem, because when they try to reach the Earth from the source of the astrophysical object, they actually get deviated by the magnetic fields in the between the source and the Earth. And this is because the proton is a charged particle, so it gets deflected by these magnetic fields. And so you can possibly never figure out where exactly in the sky that proton is coming from, because it will always change its direction. And the protons also always create these air showers just like photons, but the nature of their air showers is quite different from what photons create. So this again is a plot of the distance versus energy of the universe and different messengers. So as you can see, if you're interested mostly in the galactic center here, you can pretty much view the galactic center in any energy regime of the photons, because even until the galactic center, the universe is transparent to even highest energy photons, because it's not very far away. But however, if you move to the nearest galaxies, you say you want to observe Andromeda or something, you are restricted to viewing Andromeda in photons only up to 10 to the 14, or as I said before, about a PeV. PeV energy photons. Then the universe starts getting opaque to these photons, and the only way you can view these high energy universe objects is basically through neutrinos and cosmic rays. And here in the small here, you can see like a map of all the neutrino emitter objects that IceCube has actually mapped, and it's ever expanding from now on. So that brings me to the question that why are these cosmic neutrinos exciting? Why are these high energy neutrinos exciting? The first is that they have the highest energies. As you saw from the plot earlier, that they are mostly transparent in the energy regimes of TeVs to ZeVs. And these are zeta electron volts. These are very high energies. So what they do is they probe the physics as these new energy scales, which you can never recreate on the Earth using any laboratory. And I will also come back to that later with a plot showing the different energy scales of the cosmic rays later. And because they come from so far off in space, even the smallest effects that happen in these interesting regimes of physics can accumulate and become observable. The best example of that is the oscillation of neutrinos. So as an example, when the very high energetic phenomena happen in the universe, there are only muon neutrinos that are produced from them. There are essentially no tau neutrinos that are produced from these radiation schemes. However, because of the oscillation, when they reach the Earth, there is an almost equal ratio of the muon of the neutrino flavors that you observe, meaning you can observe an equal flavor of electron neutrinos, you can observe an equal flavor of muon and an equal flavor of tau neutrinos. So you can observe all the three flavors all from that source, even if it's not being produced in the source. And since they're weakly interacting, they don't really interact with anything between the source and the Earth, and they bring to us untainted information from these distant sources. So I talked about neutrinos, and now I'm going to cover a little bit about cosmic rays. So what exactly are cosmic rays? Cosmic rays are nothing but ionized nuclei and mostly protons. Now, it's important to note here that it's an outstanding problem in physics that we do not yet know what the exact composition of cosmic rays are. And when these cosmic rays hit the Earth's atmosphere, they create particle showers or air showers, what we call them in the Earth's atmospheres. And the cosmic rays with energies up to a few PeV, we know that they are accelerated within the Milky Way, but we do not yet know from exactly where. There has been interesting development going on very recently from one of China's high altitude detectors called LASSO, and they seem to have, they claim to have seen PeV photons coming from certain galactic sources in the Milky Way. These are called pevetrons, and this is something I work on with Veritas as well. So as I said before, these pevetrons, where they come from, they essentially come from supernova remnants. So there is some mechanism which I'll not go into detail right now, but they upscatter these photons from GeV gamma rays to PeV gamma rays, and that is how they are accelerated to such high energies, and then they reach the Earth. So the plot here on the right shows you a flux of the cosmic energy ray spectrum. So these numbers here tell you how many particles you can actually detect if you have, for instance, like a 1 meter square effective area detector. So if you have like a 1 meter square effective area detector, if you want to observe a cosmic ray with energy 10 to the 11 eV, you can only observe like 1 particle per second. And then as you move on to the higher energies, like if you move on to the knee here, and the knee is just because of the shape of the cosmic spectrum, because there's some different processes that happen which don't allow us to actually look at the exact reconstruction of these cosmic ray fluxes. And if you look at this knee here, which kind of bends down more steeply, you can see that if you have a 1 meter square detector, you can detect 1 particle per year. And if you move on to the even higher energy domains, you can see that's more like 1 particle per kilometer square if you have a detector per year. And then the highest energies, you can only detect like 1 particle per century, which of course no one is going to be able to be as, live long enough to see those. So you'd have to basically build detectors that have effectively huge areas of collecting cosmic rays, or however you detect these, in order to view a large amount of cosmic rays that come from these distant objects. And as an example, as I promised before, you can see the extent of the energies produced on the accelerators here on Earth. So for instance, the CERN, which is the Large Hadron Collider, can only produce 14 TeV protons to bash together, to collide them. And the Tevatron at Fermi National Lab here can only work with 2 TeV. So it looks like that in order to actually observe the different physics, exotic physics that happen at these high energies, you can probably never do that here on Earth. So these sources, these astrophysical sources actually give you a really, essentially a nuclear astrophysics lab, so to speak, for detecting these, for going into the details of these new physics. So moving on to the more about the air showers, what happens is when a cosmic ray hits the Earth's atmosphere, we have an atmosphere, right? So when it hits the atmosphere, there's like nitrogen molecules and the different oxygen molecules in the Earth. These cosmic rays, or I should say protons, essentially, they interact with these air molecules using the nuclear interaction models and the energy losses that happen. And what happens is that they either convert into neutrinos, which we call atmospheric muon neutrinos. They produced by the virtue of some nuclear interactions, they produce these nuclear fragments, or what we call are basically protons, neutrons, pions, and kaons. And some cosmic rays also produce these electromagnetic showers. So the one on the left here is a more of a hadronic shower, and the one on the right here shown is more of an electromagnetic shower. In an electromagnetic shower, essentially you get these the radiation of these photons by pair production. So basically these pions and kaons here pair produce into electron and positron, and then they recombine, and then they give to then they radiate into photons. So that is essentially what you observe on the Earth here. Cherenkov radiation is a special type of radiation that only happens when the speed of the particle exceeds the speed of the light in air. So we are not violating any laws of special relativity here because the speed of the light is constant in vacuum. However, in the air, it can go higher, and this is how the Cherenkov light radiation is produced. And fluorescence radiation is produced because of the interaction of these molecules or the cosmic rays with the air molecules, and they are more widespread compared to the Cherenkov, which is like a beamed emission straight to the Earth in a specific direction. So how do we detect these? Keeping the difference between cosmic rays and gamma rays apart for the time now, these are generic air showers. It can be a cosmic ray shower, or it can be a gamma ray shower, which is what I depicted as gamma ray or electromagnetic showers before. So when they hit the Earth's atmosphere, they kind of create these particle showers, the particles which I discussed earlier. And then on the Earth, there's some sort of telescopes like Veritas, which are called imaging atmosphere Cherenkov telescopes, which can actually detect the light coming from the Cherenkov light coming from these showers and work their way backwards to reconstruct the energy of the photon or the cosmic ray that actually hits the Earth's atmosphere. So you simulate, you get the light here, and then you get the energy of what the light particles are here on the ground, and then you backtrack your way towards with Monte Carlo simulations and figure out what the energy of the primary photon or the primary cosmic ray was. Veritas doesn't detect cosmic rays, but the other experiments such as flies eye here, it detects the cosmic rays using fluorescent light radiation. And there's some other detectors here on the Earth. Some can detect the radiation through scintillation counters, water Cherenkov detectors, and a good example of that is HAWC, or HAWC, which is the high altitude water Cherenkov detector, I think. And what they do is basically, instead of observing the light directly through photomultiplier tubes on a telescope, you would using when these particles actually give off nuclear reactions or interact with the water molecules inside their detectors. And we also know some of the deep underground muon detectors. The best example of such a thing is IceCube. So my work here kind of deals with the tau neutrinos coming in from space, and they kind of move through the Earth because they are so weakly interacting. They go from they go into the one side of the Earth, come out to the other side of the Earth, and then these neutrinos create, or these taus create air showers, upward going air showers in the Earth's atmosphere. So it's a very interesting idea here. As I said before, you need to have huge volumes of detector in order to observe very high energy particles, right? So what we do is we kind of leverage the Earth as a neutrino detector. So we allow the tau neutrinos to pass through the Earth, and because there's a lot of material inside the Earth that can interact with, mostly rock, sea here, the seawater here, and iron, for instance, in the more deeper layers of the Earth, it can actually interact with these molecules, and it can convert into a tau particle. For instance, the tau neutrino can convert into a tau particle. And then these taus essentially, remember I told you that the taus essentially decay to tau neutrinos. And these tau neutrinos, again, can interact with these materials inside the Earth and create taus. This is actually what is called regeneration. So it keeps happening again and again. But every time this new particle is created, it loses energy because of its collision with the other materials inside the Earth, right? So it so happens now and then a tau with enough high energy, or a tau neutrino with enough high energy, creates a tau which exits the Earth on the other side of the Earth, and they're so highly energetic that when they reach the Earth's atmosphere going upwards, they create these upward going air showers. And in principle, you can place a detector here and observe these air showers and do the same physics that you did with the earthbound detectors to figure out what the energy of the incoming tau neutrino was. So this is where I come in. I do the simulation for the propagation. Now, I'm going to introduce a concept of a satellite probe called POEMA. It's short for Probe of Extreme Multi-Messenger Astrophysics. And it is a concept mission that is designed to observe ultraviolet fluorescence using the fluorescence technique for cosmic rays and these beamed optical Cherenkov signals from extensive air showers. That's what EAS stand for. So it actually comprises of two identical observatories flying in formation. So you can see the formation of these, the satellites, I should say, here. And together, when they're separated by 300 kilometers in the stereo mode, they can observe these air showers in the Earth's atmosphere while they look down on the Earth. And it gives you enough data to actually recreate a 3D structural, a 3D reconstructed image of the air shower, and it tells you where that actually air shower might be coming from, or the source of the astrophysical object in the sky. And the other mode of operation is the limb mode, in which they're only like separated between 25 kilometers, but it covers more ground in this case. And it allows you to observe these air showers, as well as the air showers that are created by these tau decays. So as I discussed earlier, when the tau neutrinos go through Earth, they create extensive air showers on the other side of the Earth. So what this allows us to do is it allows us to study these new, the new and inaccessible energies of the universe and the particle physics. And this is probably the first, this will probably be the first satellite that we launched into the space as a multi-messenger probe. And here is a I'm not going to go into the detail because there's a ton of jargon that goes into this, but this is the simulation package that I'm a part of, which is being developed by NASA. And what it does is it allows you to measure the sensitivity of any probe, be it a space-based probe or an underground probe or a space-based balloon. It allows you to calculate the sensitivity of your instrument or your detector with which you can measure these neutrino fluxes or the values of the neutrino energies that are coming to it. So you see, we start with the geometry in which we calculate actually the geometrical variables which are required for the tau neutrinos to pass through the Earth, and then we go on to the tau propagation in which we simulate the taus going through the Earth, and this is what I do. And then when these taus exit the other side of the Earth, they create these air showers in the atmosphere, and they decay into this. And these air showers can either give rise to radio signals depending on the initial energy, or optical signals. And combining both these radio signals and optical signals, you model the atmosphere of the Earth, because there's a lot of scattering that takes place in the clouds and the ozone and the artificial pollution that's created by humans. And essentially you convert all this into the signal at the detector, at which you place wherever you place the detector at, and then you run these results and you get actual physical variables that allow you to calculate the sensitivity here. And the plots you see here are just results of the different stages of these modules that are done. Thanks. That's all. Questions?
Very cool, Samir. This was very interesting. Thank you for the talk. I would like to open the ramp for questions from the audience. If you have any questions, just raise your hand or unmute yourself.
I have a question. Earlier, you said that the highest energy photons, they scatter off the cosmic background. So if you suspect that there's a super strong source in these high energy photons, could you look for them as a signature in the cosmic background? Will it mess? Could the fluxes be enough to alter what the CMB should look like?
In principle, yes. But as far as I know, there's no probe that looks at the CMB view of the universe continuously. It's more like surveys that are taken at some particular part of time, like time period. So if you were to look, I believe if there's like a super strong source that is producing these very high energy photons, it will create a distortion in the known CMB spectrum. But then you have to have like a space probe exactly at the same time to have to look at that distortion there. Otherwise, it'll just disappear or dissipate within a few hours or days, depending on how strong the source is. So yeah.
Great. I have a few questions on the Slido app for you, Samir. The very first question is, how do we capture gamma rays when they just penetrate the telescopes because of their high energy? I think this question corresponds to the optical telescopes. Basically, the gamma rays just penetrate them. So how do you capture it?
Right. So as I said, gamma rays actually are absorbed by the Earth's atmosphere. So placing gamma ray detectors on the Earth is a very bad idea. However, what we do in gamma ray astronomy is you basically look at the showers. You look at the showers that are created by these gamma rays as they enter the Earth's atmosphere, and then you know that how these these showers progress inside the Earth's atmosphere. There's a very well-known theory for that in particle physics. So you work your way backwards, and you only get the information, the direct information of the secondary particle that actually hits your telescope. But then using this information, you can actually work backward and recreate the entire shower using models in physics and figure out what the primary energy of the photon was which hit the Earth's atmosphere. And that is how you actually get the energy of the source that it was coming from. Does that answer your question?
I think so. Yeah, that totally makes sense. Another question is, in the realm of multi-messenger astrophysics, if there was some kind of astronomical event, would we detect gravitational waves from it first or cosmic rays?
This is a very interesting question. So for cosmic rays, I wouldn't say that you would detect cosmic rays because of the problem of the cosmic rays getting deflected. So you might or might not even get anything from cosmic rays. However, there's this thing called multi-messenger alerts, which is very interesting because whenever something happens, let's say a very energetic phenomenon like a gamma ray burst happens or a gravitational wave event happens, right? Veritas gets an alert from the observatory, which observed that transient event. So if IceCube was supposed to detect a neutrino coming in from a very energetic source, it alerts Veritas, and what Veritas can do, it looks for the gamma rays coming from that source. We point our telescopes there immediately and try to look for the gamma ray counterpart from there. And if you do find like a gamma ray counterpart to them, which is the multivalent counterpart, you would probably combine your results and say that this like something is happening there. And then everyone in the other regimes of the energy spectra can actually point their telescopes and view that event. So I wouldn't say cosmic rays would be detected first. I'd definitely say the gravitational waves would be detected first if it were between the two of them. Yeah.
I see. That makes sense. One last question for you, Samir. Does Poema only detect at the specific frequencies, or does the weather get in the way? Like, what if there is lightning?
Right. This is a very good question. So there's a lot of problems when you actually move on to this atmospheric scattering here module as you see here. So when you actually, and yes, to answer your first question, it does detect at specific frequencies. It mostly detects at optical signals, which the Cherenkov light is produced in, and it looks at radio signals, which is a separate part. It's not exactly developed yet, but it's something that if you know, a mission called Anita is looking for above the Antarctic sky. It's looking for radio signals caused by these tau neutrinos going through the Earth. But yeah, Poema will be able to detect radio as well as optical. And to answer your second question about the weather, it matters a lot, because if there's a lot of cloud cover, it will hamper the detection of your air showers to a lot of extent. And not only that, but if there's lightning, it also creates a fake, I shouldn't say fake, but a background which you have to subtract from your air shower simulations. And apart from that, it also includes like the scattering, the really scattering, the aerosol sprays, which we proudly spray in the earth without giving any consequences, without having any consequences with the climates. There's clouds, as I said before, and there's also the ozone layer, which creates problems as backgrounds for these signals coming to the satellite because it's in space.
Right. It sounds like it requires very intricate modeling of all the nitty-gritty details.
Right.
Very
So here,
impressive.
actually, in this plot, you can see the threshold above which we actually discard the photoelectrons, assuming that they are created from background events. You only see the peaks that are coming here, and we only take them into consideration. So it depends on the local condition of the climate and the atmosphere at that point.
I see. Very cool. I think that answers all the questions of our audience, as well as people who posted their questions on Slido app. Thank you so much, Samir, again, for your wonderful talk. I hope everybody enjoyed it. Let's give a huge round of applause again for Samir and Brian. If you have more questions, feel free to reach out to the speaker. We will try to post the slides as well as link to the YouTube for the recording of this session very soon. Keep checking our website for more details, and hope to see you all in the next No Jargon Talk session 4.